here's the deal. Typically, one neuron will be talking to another. Sometimes neurons end right in muscle tissue, smooth muscle or striated muscle. The simple distinction that I make, and I'm no physiologist, but I play one on TV, is that smooth muscle is like inside your body. It's organs and the large intestine and the diaphragm and stuff like that. And striated muscle is the kind of muscle you work on at your athletic club.
I work on my stomach at the athletic club.
Yes, you work on the outside of your stomach.
No, I work on the inside.
You work on like your diaphragm?
I want to power digest stuff.
Yeah, good.
And be able to digest.
You're just smart enough to be difficult. You realize that? So I laugh at mine. It's funny. So the direction of neural transmission is that way, from the northwest to the southeast.
Is it always northwest to southeast?
Well, it's down the axon is the point I was making.
But is the axon always northwest to southeast?
You know the answer to that, Weisenheimer. So this is easy. And I know you're asking yourselves, well, what exactly is it that constitutes the nerve impulse? I'm going to tell you. There are two ways in which information is encoded in your nervous system. There's a, bless you, there's a chemical way, and then there is more of an electrical way. Let's talk chemicals first. You see how, we'll call this neuron number 1. See how neuron number 1
How's it chilling?
ends in the dendritic region. I just made that phrase up, but I like how it sounds. I think that's actually, it could be. Well, let's just pretend. Of neuron number 2. Well, here's the deal. There's no direct contact between neuron number 1 and neuron number 2. This will be end number 1. But this structure, which looks like like a fork, kind of like the end of a fork, which is very schematic. It comes really close to the dendrites of neuron number 2. Neuron number 1, it's called terminal endings, which I've always found majorly redundant, which is okay. They almost abut, they almost touch the dendrites of neuron number 2. So there's very little space. There's a gap. What's the gap called between neuron number 1 and bang? Say it again.
Synapse.
All right, she said it proudly, and I'm proud of her. The gap between neuron number 1 and neuron number 2 is called the synapse, or the synaptic cleft, or the synaptic gap, or gappy, or gapmeister, or gapalicious. No, it's the synapse.
Is it the actual gap or is it the fork?
It's the gap itself. It's the space itself.
Okay, so
Odd that you should name a space with nothing in it, but that's what.
is there like anything inside that space or is it just?
Yeah, intracellular fluid.
Okay.
The fluid. So this is an enlarged, this is a magnified rendering of a terminal ending. They actually do look a little bit like this under the electron microscope. It's like we're in like suction puppy, like we're in a suction puppy. And they talk like
Suction puppy.
suction puppy. Hey, I'm a terminal ending.
Sean Connery just teaches.
So like that, somewhat like that. I apologize. Okay. So inside the terminal endings are these vesicles, these little roughly spherical storage chambers. And these chambers, these little vesicles, they contain, what do they contain, kids? Sarah, what do they have inside? Great guess, not quite.
Serotonin.
Serotonin, among many other different kinds of neurotransmitters. Neurotransmitters are pretty complicated compounds that are released by the terminal endings. When the vesicles merge with the membrane of the terminal endings, they're released into the synaptic gap, and then by simple passive diffusion, make their way across the synaptic gap to, this will be a dendrite, the surface of a dendrite. Let's put it over here. This is the dendritic surface. Stay with me, kids. I know this is spellbinding. Okay. So, and these are even magnified beyond this this level of magnification. These are molecules of, let's go with what Nate said, serotonin. And here's the deal. The dendritic membrane has on it receptor sites that are specifically receptive to, specifically tailored to fit the structure of the neurotransmitter that the terminal endings are dumping into the synapse. And so you can see that the little circles fit perfectly into the so-called this will throw you off, postsynaptic dendrite, after the synapse. The postsynaptic dendrite has on it these receptor sites that are neurotransmitter specific. Neurotransmitter specific. So if I dumped, or if I could inject, if I had a tiny little needle, and I could inject, let's say, dopamine into this particular synapse, into this synapse, which really always uses serotonin, the dopamine would be hard-pressed to bind with these receptor sites, because these receptor sites are not constructed for dopamine. So different neurons make use of different neurotransmitters to help them pass along their messages. And there are different pathways in your brain that take advantage of or rely upon specific neurotransmitters and only use certain neurotransmitters. I've never gotten applause for that before.
Bravissimo!
Nate.
So each synapse
I like that
is a
lesson.
different, uses one transmitter?
One transmitter. There might be a sequence of synapses that uses the same, but each synapse uses one. That's what we're going to assume right now. Sometimes synapses are a little bit more complicated. We'll talk about that, but for now, let's make that assumption. And I think in general that's true. Is this a joke or is this a legitimate
Question.
Yeah.
Are there synthetic ways of making your brain release extra dopamine?
That's a great
and
question.
how?
Drugs.
How do I do that?
Drugs.
We can talk about that. Why dopamine, Rolf?
Because it makes you happy.
Dopamine is found
Why
in a
would you
lot
not
of
wanna be
pathways
happy?
of regulating mood. And so does serotonin, indeed. Both of them, serotonin even more than dopamine, are implicated in depression. If backing up, if parts of your brain like the thalamus that regulate mood, that determine whether you feel okay or you feel that restless, gnawing, anxious, sad feeling that probably all of you have experienced at various points in your life, some more than others. Something you inevitably feel after you experience a great loss, kind of that grief feeling, which is typically chemically mediated. If you don't have enough serotonin in pathways, so there's not enough serotonin being released into the synapse so that the message from this neuron to this one is you feel okay, you're feeling pretty happy, so that the message, like a crappy cell phone connection, breaks up. If you don't have enough of the message transporting substance that is serotonin in these pathways, you end up not feeling so great. Let's take a little diversion.
So how do you get more serotonin?
Well, that's a good question, Rolf. I'm going to address that right now. There are medications that you can take. Let me back up and first say, the serotonin's released, it diffuses across, the message is sent in a way that we'll talk about in a second, and then the serotonin is reused, it's liberated by the postsynaptic dendrite. The receptor sites let it go again, and it diffuses. Here it is, all out here. Once it binds, it's then released again. It diffuses back to a lot of it does, back to the nearby terminal endings and gets sucked back up into them so that it can be reused. There are chemicals, there are compounds like Prozac and Paxil and Seroquel and a whole bunch of them, all very closely related, that block the reuptake of serotonin by the terminal endings. They selectively block the reuptake. They inhibit it. Selective SSRIs, selective serotonin reuptake inhibitors, right? They prevent. So what happens is an impulse comes down the chute, and a whole bunch of, if it's a serotonin pathway, a whole bunch of serotonin's released into